Good morning, everyone. Welcome to Unit 2, Session 7 of Engineering Mechanics and Strength of Materials. In the last class, we are discussing about stress, strain, yield stress, working stress, ultimate stress, breaking point, and stress strain behavior of steel and strain and different types of strains. Okay, stress is nothing but load by area, right? Yield stress is nothing but the load at yield point divided by area of the section, right? Right. Ultimate stress is nothing but ultimate load divided by area of the section. Likewise, there are different types of properties which we are studied with respect to stress strain relationship of steel. Stress strain relationship of steel. Okay. And then now start with principle of superposition. Principle of superposition. Okay. Principle of superposition. Okay. What is meant by principle of superposition? What is meant by principle of superposition? Let's we study. It states that the effect of several actions taking place simultaneously can be reproduced exactly by adding the effect of each action. So, I'll read out again. Please remember, it states that the effect of several actions taking place simultaneously can be reproduced exactly by adding the effect of each action separately. Each actions separately. Okay. This is valid only when it satisfies certain conditions. Certain conditions. What are those conditions? What are those conditions? Let's we study one by one. The material is elastic. Our structure should be elastic. What is meant by that? The principle is general and has wide application, and it holds true if it has to satisfy certain condition. Three conditions. First one is structure is within the elastic limit, or member is within the elastic limit. Okay. Before that, see when we will going to apply this further. So when we have tapering sections, varying section, varying cross sections, varying cross section. When it is valid, structure is elastic. This structure should be elastic when we subject it to this load P at the either ends. That is axial tensile force. What is meant by elastic? What is meant by elastic? We are loading the material only up to which its elastic limit. Only up to which its elastic limit. Okay. Beyond, if we load it, what happens? It loses its property of elasticity. Loses its property of elasticity. Then what happens? The deformation is permanent. What is meant by deformation? Change in dimension. When the dimension will be changed, when we subject it to a forces, when we apply the forces. This effect of force causes what? Deformation. This effect of force causes what? Deformation. For all materials we are using, those are subjected to a load in such that the material deformations undergoes are within the elastic limit. Within the elastic limit. It nothing but if we are removing loading or the forces, then what happens? The deformations should be disappear, and it should come to an original shape and size. Original shape and size. This is what the first condition it has to satisfy. First condition it has to satisfy. Okay. Second condition. Let's we see that. What is that? And it has a linear relationship. Linear relationship. What linear? The stress strain relationship should be linear. What is meant by that? What is meant by that? It is nothing but when we are testing any material, stress versus strain, stress versus strain. These two are stress and strain are property of a material. Stress is nothing but when we apply an external force, there are internal forces will develop. Internal forces will develop. That is called as stress. Strain is nothing but it represents the change in dimension divided by original dimension. Strain is nothing but is a parameter which we are going to use in order to find the deformation effect. And these relations, stress and strain, if we drawn, the relation should be linear. It is nothing but the pattern in which the stresses are developed. In the same pattern, strain should be go. There should not be any random changes in the stress and strain. Then what happens? The relations will be not linear. It is non-linear. If it is non-linear, what happens? We don't have a control over the material when we load it. We don't have a control over the material when we load it. In order to avoid that non-linear variations, so we should have the conditions for holds course these principles. The stress strain relationship is linear. Stress strain relationship is linear. Okay. Next, the third condition it has to satisfy is the deformations are small. The deformations are small. There should be a negligible deformation. There should be a negligible deformation. Deformations is nothing but already I told you it is a change in dimension. Change in dimension. When we apply a load on any material, then automatically what happens? It is subjected to deformation. It may be a small to a larger deformation. So it depends upon the amount of load we are applying. But make sure that in order to validate the principle of superposition, the loading value is such that deformations are small. Deformations are small so that the principle of superposition is valid. Principle of superposition is valid. If the deformations are small, the stress strain relations are linear and the structure is within the elastic limit, then the principle of superposition is valid for uniform or varying cross section subjected to a axial loads. Uniform or varying cross section subjected to an axial load. Okay, understand this? Understand this. Shall I move on to problem one by one? Then you will come to know how it will be effect on the material. Before that, how to find out the deformations or change in length. Bars of varying cross sections. We have a rectangular cross section here attached to a circular cross section of larger size and one more circular cross section attached here with having larger diameter. See circular cross sections and it is subjected to a load P on either side axial tensile force. Okay, axial tensile force. How to find out these three different cross sections are subjected to axial tensile force P? We need to find out deformations. Deformation is nothing but change in dimension. The dimension change is only length, right? Because we are applying the loads axial directions. We are applying the loads in axial direction. Okay. So what is meant by change in length? Change in length. We have already generated a formula while finding the stress strains, right? Stress strain. Stress strains. What do you mean by change in length? Change in length. Change in length. It is given by the equation strain, right? What is that? Delta L is equal to E into L. Whereas E is equal to what? Delta L by L. whereas E is equal to delta L by what? L. Delta L is nothing but change in length. That's we want here. L is equal to what? Original length we have here, right? E is equal to nothing but what? E is equal to strain. Strain is nothing but what? Strain is nothing but what? Stress divided by Young's modulus of elasticity. Stress divided by Young's modulus of elasticity. What is meant by stress? Load by area. Load by area, right? Load by area into Young's modulus of elasticity is equal to change in length divided by original length. Then change in length is equal to what? Load into length of this member divided by area of cross section into Young's modulus of elasticity. That is given here. See, delta L is equal to change in length total. There are number of sections we are having is equal to plus or minus delta L1 plus or minus delta L2 plus or minus delta L3 plus or minus delta L, whatever the sections we are having subject to axial loads. Plus or minus refers to whether it is a compressive in nature or it is tensile in nature, whether it is a elongated or it is contracted, elongated or contracted, whether it is subjected to a tensile force or compressive force. Okay, so then what is meant by delta L? Already we have generated PL by AE in general. What are the varying parameters here? P is common force applied, is axial tensile force. L is length of the section. See, section 1 has different length, section 2 has different length, and similarly section 3 has different length. So P for first section L1 divided by A1 into E. E is common for the material of same. Here same material we are using of different cross sections and we length. See, PL1 divided by A1 into E. Similarly, plus or minus PL2 divided by A2 into E plus or minus PL3 divided by A3 into E. A3 into E. So this is the formula we are going to use to find out what? Change in length of bar of varying cross section subjected to an axial force. Subjected to an axial force. Okay. Uh, we are taking the common factor outside. Delta L is equal to what common here? P. Load is common to all the sections. And E. Young's modulus of elasticity. Young's modulus of elasticity. E is common for all the section. Common for all the section. And remaining thing is plus or minus varying parameter for different section L1 divided by A1 plus or minus L2 divided by A2 plus or minus L3 divided by A3, L3 divided by A3. Understand? Okay, this is how to find out what change in length when we subjected axial tensile force of bars of varying cross section, bars of varying cross sections. Okay. Okay. To start with the problems, if you solve the problems, you can able to know how to find out the change in length, how the behavior will be tensile or compressive in nature, elongation or contraction in nature. Contraction is nature. Okay. I'll read out the question. A bar 400 mm long is 10 mm square in section for 50 mm of its length. 50 mm of its length. 20 mm dia for 100 mm length and 40 mm dia for the remaining length. For the remaining length. Okay. Yeah, very clear cut. First one bar ಇದೆ. First total ಅದೆಷ್ಟಿದೆ? ಎಷ್ಟು ಲೆಂತ್ ಇದೆ? ಟೋಟಲು 400 mm ಲೆಂತ್ ಇದೆ, ಕರೆಕ್ಟಾ? ಅದರಲ್ಲಿ ಲಾಂಗ್ ಎ ಬಾರ್ ಟೋಟಲ್ ಬಾರ್ ಈಸ್ 10 mm ಸ್ಕ್ವೇರ್ ಇನ್ ಸೆಕ್ಷನ್ ಫಾರ್ 50 mm ಲೆಂತ್. ಫಸ್ಟ್ ಸೆಕ್ಷನ್ ಎಷ್ಟಿದೆ? 10 mm ಸ್ಕ್ವೇರ್ ಲೆಂತ್ ಇಂಟು ಬ್ರೆಡ್ತ್ ಈಸ್ 10 mm ಆ್ಯಂಡ್ ಲೆಂತ್ ಎಷ್ಟಿದೆ? 50 mm. ಸೆಕೆಂಡ್ ಬಾರ್ ಇದೆ, ಸೆಕೆಂಡ್ ಸೆಕ್ಷನ್ ಇದೆ 20 mm ಡಯಾಮೀಟರ್ ಫಾರ್ 100 mm ಲೆಂತ್. ಥರ್ಡ್ ಸೆಕ್ಷನ್ ಇದೆ 40 mm ಡಯಾಮೀಟರ್ ಫಾರ್ ರಿಮೈನಿಂಗ್ ಲೆಂತ್. ಇವಾಗ 50 ಪ್ಲಸ್ 100 ಎಷ್ಟಾಯ್ತು? 150. ಇನ್ನು ಉಳಿದಿದೆ ಎಷ್ಟು? 250. total 400 mm long, a bar. If a tensile load of 200 kN is applied on the rod, calculate the maximum and minimum stress induced in it and the total elongation. And the total elongation, take E is equal to 2 into 10 to the power of 5 Newton per mm square. E is nothing but what? Young's modulus of elasticity of material. How to find out that? Stress by strain. When we are subjecting a material for a load, then we are drawing the stress strain relationship up to the what? Linear relationship. We are finding elastic limit. What is the load at the elastic limit? We are dividing the load by area. We will get the stress, and we are finding the strain. Stress by strain. We will get the Young's modulus of elasticity. Let's we draw the diagram for this. A bar of 100, 400 mm long. Okay, 10 mm square first, second 20 mm dia, third is 40 mm dia. Okay. See 10 mm by 10 mm cross section, 10 mm squaring section, 10 mm square section for 50 mm length. Okay, let's we will next 20 mm dia attached here with next 40 mm dia, 40. Next, how much? It is 40 mm dia subjected to a tensile load of how much? 200 kN. Length is given here. See, L1 is 50 mm and L2 is 100 mm and remaining L3 is 250 mm. L3 is 250 mm. This is how to read the question and how to draw the free body diagram and then write the given data. Okay, so then how to find out this change in dimension or total elongation is nothing but delta L is equal to PL divided by AE for formula, and for 3 section PL1 divided by A1E plus PL2 divided by A2E plus PL3 divided by A3E. PL3 divided by A3E, correct? Okay, move on to next slides. This is the formula to find out the elongation of the bar. First, A1 we want 10 into 10, 100 mm square. Similarly, A2 we want, this is 20 mm dia, pi d square by 4, 314.2 mm square. Next, A3 we want, so 45 mm dia, so 1590.63 mm square. Okay. Next, what we want? Delta L1 is equal to PL1 AE. P is 200 kilonewton 10 to the power of 3. 1 kilonewton is equal to 1000 newton. So 200 kilonewton is equal to 200 into 10 to the power of 3. And then 50 L length of the first section divided by A is A1 100 mm square. E is common 2 into 10 to the power of 5. So total elongation is 0.5 mm. 0.5 mm. Next comes to second section of 20 mm diameter circular section. Delta L2 is equal to 200 P into 10 to the power of 3 Newton. Next, 100 mm length, area 314.2 into E 2 into 10 to the power of 5. Total elongation is 0.314 mm. Next, delta L3 is 200 into 10 to the power of 3 into 250. Length of the member 3 is 250 and area of the member 3 1590.63 into 2 into 10 to the power of 5. Young's modulus of elasticity. So total, the delta 3 is equal to 0.1571 mm. So total elongation delta L is equal to delta L1 plus delta L2 plus delta L3, which is equal to plus 0.975 mm plus 975 mm plus 0.975. The total elongation is less than 1 mm. Right? When we are subjecting it to a 200 kilonewton what? Axial tensile. Now, our question is not completed. Again, they are asking what? Find the maximum and minimum stress, right? We need to find out the stresses for three sections. That's P by A. Stress is nothing but P by A. Okay, here we can find out here F1 P1 by A1 is equal to what? P is 200 is common, 100 A1 is equal to 2000 Newton per mm square. Similarly, F2 is equal to 200 over 314.2 636.537 Newton per mm square. F3 is equal to P by A3 200 into 10 to the power of 3 divided by 1590.63 is equal to 125.74 Newton per mm square. Newton per mm square. Here we have minimum stress 125.74 Newton per mm square. So where we have minimum stress, there will be a minimum change in dimension or change in length 0.157. So here is a 200 Newton per mm square. Where there is a more stress, there will be a more change in length of the member is going to be expanded more is equal to 0.57 mm. So should remember that area of cross section is more and load applied is same, automatically the deformation will be small, and the area of the cross section is small, load applied will be same as the other sections, then automatically the deformation and the stresses are more, deformation and stresses are more. So write the, so maximum stress F1 is 2000 Newton per mm square and minimum stress is 125.74 Newton per mm square. Unit you have to write properly. Change in length mm, stress is Newton per mm square. I am repeating this. What is that? Without the unit, your answer is incorrect. Your answer is incorrect and your problem is incomplete. Problem is incomplete. Make sure to remember to write the what? Unit for different parameters you will going to find. Different parameters you will going to find. Okay. Shall we move on to next problem? Shall we move on to next problem? Okay. I will read out the question. A member formed by connecting a steel bar to an aluminium bar as shown in figure and calculate the magnitude of force P, total length of the member to decrease 25 mm. The value of elastic modulus for steel and aluminium are 210 GPa and 70 GPa. Calculate the work done by the force. Calculate the work done by the force. Very good question. Can able to solve this. A member framed by connecting a steel bar to aluminium bar. ಒಂದು ಸ್ಟೀಲ್ ಇದೆ, ಇನ್ನೊಂದು ಅಲ್ಯೂಮಿನಿಯಂ ಇದೆ. Shown in figure. Let's see shown figure first. See, there is a contraction. The force applied is compressive in nature. One is steel and another one is aluminium. Steel member is 100 mm by 100 mm sections and aluminium is 50 by 50 mm section. And the length of the steel member is 380 mm and length of the aluminium member is 300 mm. Okay, what we need to find out here, work done by this force P, and also we need to calculate the magnitude of force P. And they are given that the member is going in deformation of 25 mm and the value of elastic modulus of steel is given 210 GPa and 70 GPa. 70 GPa. Okay. Elastic modulus E 210 GPa is nothing but what? 2.1 into 10 to the power of 5 Newton per mm square. If you are keeping it in Newton and mm, we are keeping all the units in Newton and mm. So, and that aluminium is 70 GPa. Aluminium is 70 GPa. Okay, understand? ES is given 2.1 into 10 to the power of 5 Newton per mm square, and EA aluminium, elastic modulus of elasticity of aluminium is 70 into 10 to the power of 5 MPa. MPa is nothing but megapascal. Instead of gigapascal, they are keeping it in megapascal. Okay, then delta L is given total 25 mm. What we need to find out? The force P and also work done. Force P and work done. Correct? Force P and work done we need to find out. Work done we need to find out. See how to find out that force P. How to find out that force P. Okay, first write the area of section 1 is equal to 50 into 50 aluminium 2500 mm square. Similarly, A2 is steel member 100 into 100 is 10,000 mm square. 10,000 mm square. Then write the formula for change in length. It's equal to delta L is equal to PL1 divided by A1 E1 plus PL2 divided by A2 E2. In the previous problem when we are solving, E is constant for all the sections. Why? Because all the sections are of steel. If it is a unique material, then the elasticity will be same. Here it is a steel and aluminum, so elasticity also get changes. Elasticity also get changes. Okay, substitute here. Delta L is equal to 25, and the nature of force applied is compressive. That's why minus sign. And the P is unknown here, and the length of the PL is 380 mm. By A is 10,000 into 70 into 10 to the power of 3, right, minus P into 300 divided by 2500 into 210 into 10 to the power of 3. So what is the value of P? Calculate P. P is equal to 225.2 kilonewton. 225.2 kilonewton minus represents only the compressive force. Force applied is compressive in nature. So instead of elongation, the 25 mm here decrease in length. Decrease in length. That's what the minus sign. Our question is again one more thing we need to find out, the work done by this force. What is the work done of P into delta L? Of P into delta L. Find out this. Of P is 22.52 into delta L is 0.025. So our deformation, so total work done is equal to 2580 Newton millimeter. Okay, this is how to solve the problem. Yeah.